In this video, we're going to look at some of the general aspects of hypothesis testing and then begin to apply them to t-tests. In general, we'll have the same steps for our hypothesis testing throughout the rest of the course, but we will be applying them in different research situations. It's worthwhile to see the general procedure before we get to the specifics. In general, all of our hypothesis tests have 4 steps. In the first step, we state the null hypothesis, which is the situation that we would expect to have if our independent variable or our grouping variable did not have an effect. And then we state one or sometimes more alternative hypotheses. Once we've stated those hypotheses, we decide before we compute anything what alpha level we want to have, which can also be thought of as how much risk of a type 1 error we're willing to make. Another way of thinking about alpha is how far from the situation described by the null hypothesis does the test statistic need to be before we're willing to reject that null hypothesis. In the third step, we'll compute the test statistic. Right now we're looking at t, but soon we'll be looking at f for analysis of variance, r for correlation, and the chi-square statistic. And for each one, we'll also be looking at its p-value, which is the probability of getting this exact result if the null hypothesis were true. Once we've computed the test statistic and found a way of looking at its probability, the last step is to make a decision, either to reject the null hypothesis or to retain it. If we reject the null hypothesis, we go on to compute an effect size, and we might consider computing a confidence interval or some other kind of estimate, as mentioned in the textbook. So those are the steps and the options that will be with us for the rest of the course. It's definitely worthwhile to memorize that sequence because we will be doing it so often. The next slide here shows us a graphic vision of how this happens. If we look in our t statistic, we have already been looking at something that's somewhat like a normal curve with the high probability values, the things that would be likely to happen if the null hypothesis were true. And so if our result is somewhere in that region, we retain our null hypothesis. But if we get a statistic that's far from zero in the positive direction or far from zero in the negative direction, that says that we're looking at a result with a low probability. Remember, the height here is a frequency, so it says this would happen only a small number of times compared to the things in the middle where the mean is. These would happen a large number of times. So out here in the tails, it's a low probability of happening. When we get to analysis of variance, we'll be using a different curve. It's an F curve, but there will still be a critical or rejection region whose area is defined by alpha. And the same is true with our chi-square statistic when we get to that point. So no matter which statistic we're working with, there will always be an area that's defined as high probability. It's usually left blank. And then another area that's defined as low probability if the null hypothesis were true. And if our statistic falls in this area that would be unlikely to happen if the null hypothesis is true, then we say, well, I guess the null hypothesis is not true, and we reject it. Once we make the decision, we can also say, what is the exact probability of getting the result that I found? So in this situation, I'm looking again at my t curve, and say I had a t statistic that fell at this point. If I drew a line and looked at the area to the right beyond that t point for the actual t statistic, that area would be the exact probability in one tail of getting a result that extreme or or even more extreme. So the blue area is saying, here's where my critical region starts, but if I'm rejecting the test, I might want to know what's the exact probability. If I wanted to know a two-tailed probability, because the curve is symmetric, I would take this number and double it. When we're using the tools that are in our textbook, we don't have a way of getting this exact probability. But when we're working with Microsoft Excel, we'll find that in fact, the first thing that Microsoft Excel gives us is this probability, and then we have to use that to find the t-statistic. So we'll be able to get that exact probability quite easily. In this part of the course, we're looking at three different kinds of t-tests, so I thought I would describe them all and then look at just the first kind in this video. The first kind of t-test we call a one-sample t-test, and an example of that would be if we were trying to explore whether there's evidence for what they call a cancer cluster. If it seems like there are more cases of cancer in a place than would be expected according to the general population, so we would have an average cancer rate in that region and compare it to a population-wide number. The second type of t-test looks at having independent samples, two different groups. So for instance, we might compare the salaries of nurse practitioners and of physician's assistants and see if those two groups of practitioners differed significantly in their salary. The third kind of t-test is one where the samples are related, and it may be that they're paired, meaning that we take measures from two different people and look at their differences. So we might ask, do moms and daughters have similar IQs to each other? Another kind of related samples test is a repeated measure, where we measure the same person twice. For instance, is self-esteem higher before passing a difficult test or after passing a difficult test? So we would measure before and after, and then for each person we would subtract the before score from the after score and get just one different scores. So those will be our three types of t-test that we'll be working with in this segment. The one-sample t-tests are very much like the z-test that we already looked at. We need a t-test if we're in one of two situations. If our sample size is small, which is usually defined as being less than 25 or sometimes 30, or if we don't know the population standard deviation. And that's the usual situation. We might have a hypothetical mean to compare to, but we often don't know the standard deviation. The formula for our one-sample test uses an estimated population standard deviation in order to calculate the standard error. So in order to use that estimated standard error, the first thing we need to do is compute the standard deviation. In most places, we'll see that represented by S for the sample rather than sigma, which usually stands for the population. Our book uses sigma as though it's for the population, and then EST to show that it's an estimate. But if you remember, we've got our sum of squared differences from the mean on the top, and then what makes it a sample standard deviation is the fact that we're using n-1 on the bottom. Once we've computed this estimated standard deviation, then we can use it to create our estimated standard error. So we take that standard deviation and divide by the square root of n. And this estimated standard error is what we use in computing our t-statistic. So we're going to need to determine a rejection region. It can have a two-tailed version, meaning that we're looking just to see if we're different from the mean, and it could be different in the positive direction or different in the negative direction. When we're looking at a directional test, for instance, if we were looking for a cancer cluster, we probably wouldn't be caring whether cancer rates were lower than average, we would just be trying to detect a higher than average rate. So we would really want only to reject the null hypothesis if we found excess cancer rates. In another situation, if we were looking at whether a drug or a vaccine affected a cure, we might be looking only in a negative direction. So our directional tests direct our rejection region to just one portion of the curve. When we don't have a very solid, really sure reason, it's safer to run a two-tailed test, which would detect a change in either direction. Our t-distribution looks a lot like a normal curve until we stack them up. Our normal curve is the highest one here, and we can see it's high peaked, and then it slides down and has what they call narrow tails. And the t-curves are based on the sample size, so a sample size of 5 is flatter in the middle, and the tails are higher on the end. Now you might wonder, what difference does it make how high the tails are? But remember, we're needing to get 5% or less of the area. So if it takes a long time for the tail to get close to the axis, it means that we need a larger and larger t-value to get to that critical point. That's what we've got for this introductory part. In the next video, we'll be looking at 2 sample t-tests. It will still have those same 4 steps that we looked at in the beginning.